So right now we're talking about resistance in Cartesian coordinates. Let's think about resistances in other coordinate systems. So remember, we derived the expression for like a constant AC. If we don't have a constant AC, what happens? So let's actually go through this derivation. I'll do it kind of quickly because I don't think the steps are really that important for now. What's really important is seeing the result and seeing where the resistance comes from. Okay, so let's see. Let me actually start with this. So if you have a resistance in cylindrical coordinates, R cylindrical, the resistance, instead of it being thickness over K times AC, is actually the following. It is the log, which I'll write ln, of R in over R out, divided by K times 2 pi L, where L is like the depth into and out of the page. Okay, so that's, I guess, the goal. So we're trying to figure out how to get to that. So we have to go through the steps to derive to get to that resistance. All right, so here's our cylindrical coordinates. This is our control volume. Let's go through the analysis again quickly because we've kind of done this. So Q dot at R, we have Q dot at R plus dr, and then the width here is dr. So we do our energy balance, Q dot R minus Q dot R plus dr is equal to 0. We substitute in Fourier's law, so this becomes, we do the Taylor series expansion, so this becomes Q dot R minus the quantity Q dot R plus dQ dot R dr is equal to 0. So this simplifies to dQ dot R dr equals 0. Right? Again, that kind of makes sense. We're not losing heat or anything like that. All right. Now we substitute in Fourier's law. So for this one, it is Q dot is equal to minus K AC, which is a function of R, times dt dr. So let's write that out. It's minus K 2 pi R L dt dr. Right, again, just a couple things to pay attention to. So L, again, is the distance into and out of the page. It's like the length of the cylinder. In the resistance model up there, you see that there's R in, there's R out, and then we also have R appearing down here. So just want to make it clear, we're talking about, after we enforce boundary conditions, that's going to be at some radius R in, that's the boundary of the domain, and we have some other radius R out, that's a boundary of the domain. Those two things are known values, right? Those are specified values. R is the independent variable, so R is the thing that's changing in the domain. Okay, just want to remind us of that fact. Okay, so we're going through the steps here. Let's just keep going. So let's take Fourier's law and plug it in. So we end up with dQ dot dr. So dr of this whole Q dot thing, so minus K 2 pi R times L times dt dr is equal to 0. Let's see, minus K is constant, 2 pi is constant, L is constant. So that simplifies down to ddr R dt dr is equal to 0. Incidentally, there's a question in this situation. R is the independent variable. Can we bring R outside? Right? Is this the same thing as saying R times d squared t dr squared? Hopefully I see a lot of this, right? No. You can't take the R out because R is the independent variable. Right? So if there's confusion about that, you can't do it. So to solve this equation, we have to bring that dr over to the right-hand side, integrate, and then deal with the R that's on the inside. Okay. So let's do that. We're going to integrate this, so we get the integral of dr dt dr equals the integral of 0 dr. So that's r dt dr equals C1. Integrate again. We'll divide by r and then integrate again. So we have integral of dt is equal to the integral of C1 over r dr. Okay, and then ultimately we're left with temperature is equal to C1 ln of r plus C2, right? Integral of 1 over r is ln of r. Okay, so this is a different solution than the plane wall solution, right? It's not linear. That's fine, right? But it's a different solution. So we've gone through the derivation, we got to a different solution. Now we have to again enforce the boundary conditions and see then where this resistance idea comes from. So let's quickly do the boundary conditions and then we'll kind of move on to convection and radiation resistance. Okay, so boundary conditions, again, for the resistance one, we're going to think about it only the temperature boundary conditions. So we're thinking about it like we're specifying a potential. We're solving for heat transfer in terms of this resistance. So the boundary conditions are BC1 is T R equals R in is equal to T H. BC2 T R equals R out equals TC. Okay, so if I plug this stuff in, let's see. Yeah, so let me just plug this in. So we saw, let me skip a step because I don't want to bore you guys too much. So we'll plug it in, and then we're going to solve for temperature, and I'll just give you the solution for temperature, right? You can trust me that if you plug in the general solution at the top of the screen into those, and then solve for the constants, it's going to give you this. T as a function of R is Tc minus Th times ln of R over R in divided by ln R out over R in plus Th. So that's our general solution in cylindrical coordinates for specified temperature boundary conditions. Okay, and you could put a box around that if you want. This is the kind of thing you can like look up in a textbook and have that. Where we want to go again is the resistance. So we need to express this for Q dots. We need to take the derivative. So let's take the derivative. I'll plug it in. Again, I'm going to skip that step because I don't want to make you write too much. But we get Q dot is equal to this mess. So K times 2 pi L over ln of R out over R in times Th minus Tc. All right? So again, this looks like Q dot is equal to some potential, Th minus Tc, plus some stuff multiplying it. And that stuff is the resistance, or the inverse of the resistance. Okay? So this thing here is a bunch of constants. This is 1 over R, which we'll call R cylindrical. Okay? So that's where that comes from, right? I mean, it's just walking through the same steps in a different coordinate system. You're left with a bunch of constants multiplying a potential. That's your resistance. Okay? Questions on that? Okay? Let me give you the spherical coordinates one, and then we'll wrap up with a couple other resistance. So the exact same analysis, R spherical, you have 1 over R in minus 1 over R out divided by 4 pi times K. So that's, if you happen to be using spherical coordinates, that's the conduction resistance in that problem.